In this video, I will be presenting a design for a hyperspectral imaging system for near-infrared detection of nitrogen and organic material in soil. Before I get further into this project, there are two key papers that were important in the development of this design. And so the first is the measurement and analysis of soil nitrogen and organic matter content using near-infrared spectroscopy techniques. So as seen in the images on the right, the top image shows the nitrogen predicted in a sample based off its spectroscopic information, and the bottom shows the actual nitrogen measured in the sample. And so the idea here is you can use predicted nitrogen values to determine the amount of nitrogen and organic material content in soil. Additionally, the design was based off of the line-scan hyperspectral imaging framework for open-source low-cost platform. In the first paper, the reflectance spectra of a sample of soil, as well as its corresponding absorbance spectra, were both shown and analyzed. There are particular organic matter absorption wavelengths, as seen in these images, that show up in both the reflectance spectra and its derived absorbance spectra. This holds true for nitrogen as well. There are particular peaks that correspond to nitrogen concentrations in soil that can be seen in the absorbance spectra. These key wavelengths allow us to determine the quantity of nitrogen and organic material that is present in the soil sample. A sensor was selected to span the range of these spectral peaks, from 900 nanometers to 2400 nanometers. For this design, the Sony IMX990 short-wave infrared image sensor was chosen. The important features for this design were its sensor unit cell size of 5 microns by 5 microns, its height of 5.8 millimeters, and its pixel spacing of 11 microns, which determine the maximum possible resolution capable using this sensor. Hyperspectral imaging techniques have certain strengths and weaknesses. In particular, there are three general types. There are push broom scanners, which spatially scan over time, band sequential scanners, which acquire spectral information over time, and snapshot imagers, which generate an image from one moment in time. And so these allow for gathering information across a whole spectra instead of in just the RGB that's typical with RGB sensors or cameras. So this effectively is taking in a light source and spreading it out over the entirety of a sensor, ranging from the highest wavelength to the lowest wavelength. In this particular design, a push broom scanner was used. So, to summarize the design requirements, the wavelength range was specified to be from 900 nanometers to 2400 nanometers to capture all relevant spectral absorption lines for both nitrogen and organic matter. Additionally, the object and image locations were defined. The object is considered to be at infinity and the image at 16.5 millimeters from the back of the final lens element. And this was done to maximize the usage of the sensor dimensions. The spot size should also be diffraction limited to avoid overlap between the sensor elements, and the spectral resolution was selected to be 10 nanometers. This means that spectral features from the absorption peaks mentioned in the first paper of 30 nanometers will be clear in the spectral scan. This results in a spot size of about 4 pixels or 4 microns. Additionally, as this design is intended to be a handheld device, a total track length of less than 15 centimeters was selected, and for relatively fast throughput, an f-stop of 6 was selected. The primary choices for optical materials in the project were calcium fluoride and magnesium oxide. Both calcium fluoride and magnesium oxide have a fairly constant index of refraction from 900 nanometers to 2400 nanometers. Additionally, calcium fluoride was selected as it's fairly inexpensive to work with compared to other infrared transmissive materials. Magnesium oxide is more expensive than calcium fluoride, but it became necessary to include it in the project during the final iteration of the design, as it was needed to create achromatic cemented doublets, and it was needed for its higher index of refraction. For the first order design, and based on the second paper referenced, the design on the right was created. This is a push broom sweep-based hyperspectral imager. It consists of an imaging lens, a field stop that represents a narrow slit for reducing the image to a narrow object band to be swept, a collimating lens, 2 prisms, one to direct the incoming beam down to a diffraction grating that's in the center, and another prism to direct only the first order diffraction spot back to the optical axis. The 0th order undiffracted light is sent out of the system. Then this first order light is sent to a focusing lens to turn each wavelength packet that is at a different angle into a different spot located along the sensor's y-axis. The important parameters here are the diffraction grating period length, the focusing lens focal length, the imaging lens focal length, the collimating lens focal length, and the prism angle. Additionally, a bit of a sanity check was performed using an online simulator. The 2-prism and diffraction grating system was set up along with the imaging lens just to verify that the 0th order light would be diffracted out of the system, and the first order light would maintain its position along the optical axis and be imaged at the imaging plane properly. After the initial first order design, Zemax was used and the first order setup was created with the following lens data. After the first order design was entered into Zemax, the following spot sizes were found. As a note, 6 wavelengths were tested in the system from 900 nanometers to 2400 nanometers, with a spacing of 300 nanometers between each wavelength. The largest spot size was found to be around 80 microns, and the smallest was around 25 microns. One of the biggest problems in this project was due to the uneven wavefront of the incoming light. The dark blue bundles of rays represent the 900 nanometer light, while the cyan bundle of rays represents the 2400 nanometer light. As can be seen on the curve, the wavefront is highly asymmetric. And as can be seen in the figures below, the wavefront is not only asymmetric but highly curved as well. This results in a system that is difficult to optimize, as while a single ray packet can reach diffraction limited spot size, the other ray bundles cannot be optimized because they'll always be at a different curvature. This was fixed, and I'll later go over how it was fixed, but after the fix, the curvature on the right, representing the final result, was greatly improved. I also want to draw attention to the scale bars. The maximum curvature on the left is about 24, and the maximum curvature on the right is about 4.5, showing a reduction in the most extreme values of about 5 times. Additionally, the scale bar on the left image is at 5 millimeters, and on the right, this is 2 millimeters, showing a significant reduction in the curvature that can be easily seen. The primary cause of the wavefront curvature issue in the initial design was due to the significant chromatic aberration that occurred in the first 2 lens elements. This chromatic aberration propagated through the rest of the system and caused significant wavefront curvature by the time that it reached the sensor. To compensate for this, the first 2 lenses were made into achromatic cemented doublets, using calcium fluoride for the positive lens element and magnesium oxide for the negative lens element. With this, the chromatic aberration could be reduced to insignificant levels and a fairly flat wavefront curvature could be achieved. So here were the key Zemax optimization techniques that were the most helpful in this project. The most important optimization feature was checking the ignore lateral color box. So this is in the optimizer wizard, and when unchecked, the merit function is set up in a way to try and reduce chromatic aberration as much as possible. However, it only does this at the imaging surface. So it doesn't do this anywhere else in the system, just the imaging plane. So this could be really useful in a system where you're trying to reduce your chromatic aberration as much as possible. However, in the system, the goal is to separate each wavelength as much as possible and spread it out over the entire sensor. So if the ignore lateral color box is unchecked, it causes extreme changes to usually, for this project, the last lens element in an attempt to refocus all of those distinct wavelengths to the same spot, really negating any other form of optimizing. In a standard system where you are focusing to a single spot size or a standard imaging system, not a spectrometer, leaving this unchecked, having the lateral color corrected for, could be very useful. Additionally, the other key features for ZMAX optimization were using the minimizing RMS spot size settings from the merit function wizard, as the goal of this project was to get the RMS spot size as small as possible. This worked rather effectively for trying to minimize the spot size on each separate wavelength that was modeled. Additionally, an air gap restriction between 0 and 40 millimeters was stated, and in the merit function editor, the CVGT, curvature greater than, and CVLT, curvature less than, for limiting the curvature from extreme values were also utilized. And primarily this was to avoid any extreme values and local minimums that tended towards extreme values. In particular, one thing that was a struggle during this project was that the first lens element tended towards an extreme minima. Just as ZMAX attempted to minimize that spot size while also ignoring the parameters I had set for the spot size height. And so by setting these limits, I could prevent this from going towards extreme values. Here's an overview of the final measurements of the system, including the addition of the achromatic cemented doublets that utilize the magnesium oxide. And this is the final design. The final spot sizes were also minimized in the final design. And so each of these spot sizes is smaller than the Airy disk, showing that this is diffraction limited. Additionally, you can see that there appears to be significant aberration on several of these, such as coma. However, these are all actually fairly small values compared to the overall spot size. And so each Seidel aberration was at its maximum 0.003 wavefront errors. So additionally, a tolerance analysis was performed for this system, and it was found that this system is highly sensitive to decentering, which makes sense considering that any significant amount of the decentering, especially in the first two lens elements, will result in rays that are no longer passing through all surfaces, which was the primary issue. Additionally, the surfaces 1, 2, and 4 were also determined to be the most sensitive surfaces. These are all surfaces that are in the first lens element. This is at the beginning of the system, and any aberration that is present in the first lens causes significant deviation through the rest of the system. And this was also the most difficult to resolve issue during the building and optimizing process, where any significant changes to the first element of the lens caused extreme aberrations. Overall, though, the system was fairly insensitive to surface thickness, but highly sensitive to the X and Y offset. So the instability is likely due to the increased chromatic aberration in the first two lens elements of the design, which is also where the primary issues occurred. This can also be seen in the tolerance analysis, where the RMS spot radius increases extremely, and this is due to the rays missing the final imaging surface. So in terms of practicality and problems, all of the components are physically possible and machinable. And tolerance analysis suggests that the X and Y offset is problematic, so this requires a fairly high degree of precision with the placement. One issue in terms of practicality is just how expensive the system will be. The material is definitely going to prove more expensive than the standard crown or flint glass used for visual imaging systems. As this is near infrared, these materials are just used less, and so they have a higher price tag. Additionally, the selected sensor only covers the spectrum from 900 nanometers to 1600 nanometers, which means that an additional sensor is needed for this. And a simplified design could be considered, utilizing concave mirrors to focus incoming light and the first order diffracted light, which would replace 4 of the refractive elements, the first 2 lens elements and the 2 prisms. And this could greatly increase the price point, but also change the overall design, as including mirrors in there would require the system to have off-axis elements. In conclusion, the system objectives that were defined earlier and the design specifications were met by the system. Tolerance analysis found a high degree of sensitivity in the first lens element, and additional sensors are needed to be found, and the system needs to be redesigned to meet new sensor specifications. Thank you for watching.